next speaker is Shen Tsai for Tokyo University of Science and RIKEN.
Okay. Okay, here. Let me thank the organizer for inviting me here. Very happy to be here at the 41st floor. This is the highest place I give a talk in altitude. And my topic is quantum annealing, of course, the topics of this conference. And I will talk about quantum computing and quantum simulation as well. All of them are based on something related to the photons. Of course, everything is based on superconducting circuits. Oh, I can't use this. So here's a family tree here. Superconducting circuits, quantum circuits. And it started in 1999 at NEC. We made the first charge qubit. At the time was Nakamura, Pashkin, Tsai. And a bit later, we have, oops, sorry. Here. It's very hard. Let me change my hand. Phase qubit and flux qubit slightly later. And of course, now we have much larger system, and with Google, IBM, and D-Wave having much larger system, and many other industry are jumping into the business. It's a huge community for this superconducting qubit. In the meantime, NEC and RIKEN, which we are collaborating, decide that our lab at Tsukuba was too expensive. So they stopped the lab. So I had to, so the member was dispersed, and I had to move the lab from Tsukuba to RIKEN in Wako and also university. So now I'm building up two labs since 3 years ago. And of course, this is what Oliver showed. The decoherence time, T1 and T2 are increasing as the time goes by in all these years in exponential fashion. It may be like twice, increasing, many degrees of magnitudes. And use this. And now we have, something even reaching millisecond. And we started here roughly, it's a fraction of nanosecond. The first charge qubit was very short-lived, but we learned how to increase the decoherence time with many tricks. Yeah, okay. Yes. And in terms of gate-based system, you need fidelity, high fidelity, and then this high fidelity is realized. This work was Will and NEC, and then we have even 2 qubit. We have very high fidelity to do surface code quantum error correction. In just one step at each time. And okay, in this talk, I'll introduce, well, maybe circuit QED, something similar to cavity QED, developed with atomic physics. you have atom with a very high Q cavity, and you do state control in this system. And the circuit QED can mimic this atomic system. We can have sigma x, sigma y. This is a cavity with just a resonator, superconducting resonator. You couple qubit. In this particular case, I draw a flux qubit. This is with alpha loop. And also ion trap system you have. We can mimic that too with sigma z coupling. And this is easily tuned or changed by changing the circuit configuration. This is the strength of the artificial system. You can, there's a large degree of freedom you can play with. And the first topic I'll introduce, I mentioned I have 3 different topics, and each funded by different program. Since, as I said, in quest of funding, I applied for many things, and I have 3 fundings, and they all have different directions. So this is the first thing I introduce. It's funded by NEDO project. Somehow it's cut off. Yeah, Q was missing here. I don't know why. So I have a bunch of qubit and spins. And we're in this particular project, we're thinking of long-range coupled quantum annealing system. So you have a strings of n qubits and spins. How about considering some full coupling scheme? And we have this bus system made of resonator, and you have coupler here, and you can have full coupling, perhaps in extreme cases. You have about n squared half number of the couplers. And so we started to think about this kind of system. And of course, yeah, sorry about this cutoff. The resonator has to be made by lump element resonator, because if you introduce coplanar time, you always have standing wave. And you cannot place all these coupler at any place that you like. So we try to look for non-standing wave type of resonators. And my student at university are designing these things. Sorry, before that. So these are different type of coupling, possible sigma x, sigma y, sigma z type of coupling. And coupling, so this is basically what we want to do. You have this is the resonator. One resonator is coupled to 1 qubit, and that is coupled by a coupler. And the effective coupling, you can generate sigma z coupling. Of course, you have, the coupling is higher order, so the question is how strongly you can couple this to qubit. And we are thinking of, to enhance all these self-inductance coupling, we can introduce, in extreme case, you introduce Josephson junction self-inductance, which increase the self-inductance of these lines very much. So that's another possibility we are thinking ahead to increase this effective coupling strength. And this is another case where you have sigma x coupling. This is cut off again. You have 2 sigma x, and as a result, I expect to get sigma x, but somehow we get sigma x, sigma x, plus sigma y. And but anyway, you have all these possibility to play with different couplings. So this is the first generation lump element LC resonator we designed. So it consists of 2 parts. Inductor part is edge-coupled inductor, and then you have interdigital capacitor. I have 2 designs here, as for example. And the Q we measured. Sorry about the cutoff. The niobium film we used was not very well. This is just common niobium film built on silicon wafers and doped. It was thick SiO2. So this is well, this is something like 10 to the Q of 10 to the minus 4, I believe, and 3 minus 2 or something. So when the photon level is small, like if 1 photon level, we have like 10 to the minus 4 level. I'm sorry, this is 4, 5, 6, or something like that. And so with better niobium film, better substrate, we are looking for something better, expecting something better. This is simulated, okay, this is frequency and S parameter measured, or not only measured, simulation, analytical calculation, and measured. And it shows we have 2 designs, as I have shown, resonator 1 and resonator 2. Resonator 2 has 2 modes, first mode, second mode. And resonator 1 has just 1 mode. And both resonator has the measured value agree with analytical calculation and simulation. And this particular one, resonator 2, has some standing wave element. But you know, as long as you don't cross this level, maybe we're safe. This is the line shape. Okay, so and we're designing using this resonator. We put 4 qubits. We haven't done we just made this sample. And okay, we have we just put transmons here. And here, this is C, and this is L. So we'll see what happened. Maybe we can have a result next week to be characterized. We tried to do this before this conference, but somehow the fridge went down and it didn't work. So, okay, this is, sorry for the Japanese. It says on-demand, tunable microwave, single photon source. This is different subject. Something to do with using superconducting qubit, produce photons, and then read photons. Okay, so this is 50 ohm transmission line. And at the middle, we chop the transmission line to half. and connect that by a flux qubit. And flux qubit is coupled to each half of the open space by capacitor. So you apply pi pulse, and then with the decay of this qubit, a single photon is emitted to one particular direction because capacitance here is much larger than this capacitor. So close to 99%, the photon will flow into this half space and get detected. And okay, we look at the G2, the correlation, and we see anti-bunching. Very nice. We still have a lot of noise in measurement, but we see a clear anti-bunching. And tunability and the efficiency is shown here. We can tune from 9.5 gigahertz to 10.5 giga with efficiency of about 80%, roughly. We expected to have something higher. We don't know. Somehow energy is dissipated someplace. We are still looking for what's happening here. And also, the detection scheme is not very efficient. We are not using anything fancy, just low temperature cryogenic amplifier. So the signal to noise level is still really large, so we have to average a lot. So the next generation of this experiment will need to use microwave single photon detection technique. Okay, this is Rabi oscillation in this system, and this is line shape. We have this photon has delta omega this width, and which is related to T1 time. This is T1 time measurement, and oops, sorry. So it shows so this width is defined by this T1, and which is rather short. I believe it was like 10 or 20 nanosecond, because these are strongly coupled to the qubit. And the second generation, the previous one is used flux qubit. Now the student designed a transmon type, which may have an easier wiring in the future. So, and in this scheme, a single photon will come out. So this is looking at the normalized transmission. And so this x-axis is external flux. By changing flux, you can change the frequency of transmitted light. So you see the lights coming out here. When the system, it's not with resonance with the qubit, everything is dark, so there's no leakage. And the only time lights come out is because you have a resonance with the qubit. And we have particularly strongly coupled location. Lots of photon comes out here. And at this level, looking at Smith chart, we can infer with particular, if you increase the driving photon, you start to have lots of decays, but with small number of the input photons, you get about 85% photon generation efficiency. Okay. And this is Rabi oscillation. Yeah, still the T1 is short because two leads are strongly coupled to the qubits. The input leads actually can be made weaker coupling. We haven't done so. But, and another experiment we carried out is in this particular case, we have a flux qubit, again, coupled to the resonator. Eventually, I'll show you why. But, we want to couple this to the resonator. And this has been done in many groups, but anyway, we have transmon with cavity. You have a nice coupling. This is rather hard to see, but if you expand this part, you see avoided crossing, and you see the coupling strength is about like 80 mega. And in this particular experiment, we look at not only two-level system, we drive three-level system atom. So try to see this outer towns splitting, which is the classical outer towns splitting was demonstrated in 1955. So, which means the physics is simple. You just, if this drive is strong enough, this two-level splits, and you have this rest states. And if you look at any of this, this transition or this transition, you see splitting if the level. And in this particular case, we have a cavity. This is new with some coupling constant. And in this result, we have some interesting result. Experimentally shown, even the driving is small, you still have coupling. This is vacuum-induced splitting due to this coupling because of the vacuum. So classically, you have the splitting, but this axis is photon number. If the photon number is small, you should have one level, but still, we have a splitting due to vacuum. And this is shown by simulation. And this point is about photon number 1. The average photon number here is 1, and this is 2. And this is quantum regime. You see this vacuum splitting. And something like that, perhaps we can, using that to demonstrate some sort of application to single photon device in the future. Microwave detection. There are so many single photon detector based on superconducting, or not only superconducting system, in the visible light range. But in microwave frequency, the energy is like 10,000 times smaller. So you have to be very careful. It's very hard to detect small energy photons. And what we do, sorry for the Japanese, I have here a resonator again, and you have a qubit, flux qubit, and this result was published last year. And since you have a resonator and photon qubit, you have qubit states and photon states, and you have this is higher photon states. And Okay, I thought there was another slides before. But okay, if you drive this qubit with right amount of power, and you can induce this impedance matched lambda system, which means with 100% efficiency, you can send the states to this state, and then the photon incoming photon was absorbed, and then you have frequency down converted photon comes out here into the resonator, and at the end you send the states to this excited states of the qubit, and you read it out, and so you do the single shot readout of the qubit, and finally we demonstrated that you can read out the photon with efficiency of like 70% roughly, and this is limited by the T1 time of this qubit. So this is deterministic state control of single photon. So a single photon can drive the qubit from 0 to 1. So this is very exciting system. And one of its applications is single photon detection. Oops, what's this? Okay, I'm missing something here. Another, okay, was this. So why we're, so now let me discuss what can we apply for these single photon creation and single photon detection. One proposal we put out for this CREST project, which we just started, is quantum computing based on photon-based quantum computing with superconducting circuit, QED, which is, so we have a superconducting system spits out microwave photons forming cluster states called machine gun. And we do, so this will produce entangled photon in time space. This is space and time. You have entangled cluster states, and you do the measurement at one point using also superconducting based system. You can do universal quantum computing based on superconducting system, and this is what we are trying to look into, this problem. So the basic element is you have a single photon generation and single photon detection, and so these two processes are described as I just did, and this can be improved, and you have to entangle both the source and perhaps also at the detection. This will enhance the efficiency of the readout, and scaling can be done in linear way, bilinear array of qubits and the resonator. And so you can produce this entangled photon qubit. So we're searching for scalable architecture, and with collaborating with Cirrus, we're thinking if basically this can be expand to do the error correction. And so this is what we're looking for in this project. And this project also involves AISD group to help us looking into this large-scale integration of this kind of qubit. This, by the way, this bilinear array architecture is rather similar to this IBM 16-qubit array announced just a few weeks ago. And last, quantum simulation. I'll talk about this at the end. And we look into some simulation system. This is based on another project. It's called Impact. And at RECAN, we are supposed to think about something about quantum simulation or building a quantum simulator. And we were scratching our head, what is the most efficient way to build some sort of simulator, simulating something interesting. And then we come up with this Nature Photonics paper by Harvard group. They come up with boson sampling circuit to do quantum chemistry simulation. And this boson sampling, you have photon source, and this is beam splitter, and then you count the photon in the channel. And very fast, Scott Aronson proved that, if this is complex enough, you cannot track this by computer, modern computer. You need quantum computer. And here, so you shine photons in and count. So it's very similar, they argue, this Harvard group, saying this can be seen by shining photon into this ensemble of molecule, and then looking at the splitted out photon. And so you excite the photon, and then you see the excited mode. And so this is spectroscopy of looking at the vibronic states. And this can be, this is important part of this quantum chemistry. And if you can build this, you can do quantum simulation of vibronic states of the complex chemistry, chemicals. And in this case, N is number of the photon, and M is the optical mode. In this particular simulation, you translate that to the vibrational mode of the chemical. So using superconducting states, again, you have a qubit and a resonator, and resonator can be coupled by some sort of coupler. Coupler is here as a beam splitter, and resonator is a photon pass. A superconducting qubit acts as the photon source and also the detector. We can detect it here, or also you can use the same qubit, perhaps, to read it out. And how large the system we need to do something useful. A number of the photons required. I was told this can be tracked by the Racer's algorithm, calculating this function. And this is the chart showing how many photons required. And this is the chart. With this computation is done by the fastest supercomputer, Sunway Taihu Light in China, someplace. And it shows like with 80 photons, it takes more than 5,000 years for this guy to solve. So I assume 70 or 80 photons is the point that we want to do. And number of the resonator, number of the mode, Scott Aronson's proof with n has to be larger than n square. So these numbers square, this number of the cavity you need. And we are thinking that we can do better just by something close to n, like, you know, putting 80 resonator, maybe we can already do something interesting. So these are plans. And here's my summary. We have few, okay, quantum annealing. This is supported by NATO project, looking for long-range coupling. And universal quantum computer, we use cluster states. This is cutoff, funded by another agency. And impact is, under impact we do boson sampling, quantum chemistry, we're trying to do. And as the basic element, we have single photon on-demand source, single photon detection, single photon deterministic state control, or something like that. And we are in need of postdocs. And thank you very much.
We have time for a few questions. No questions?
So I didn't quite get in the boson sampling architecture. So the main problem doing boson sampling optically and scaling up is you have to get all the photons into the linear optic array at the same time so that they all overlap with each other. Do you have that problem here? Can you create these microwave photons on demand so that they all get in at the same time? Or by the fact that you're using resonators, does that mean that you're all right?
Yeah, so you inject photon one by one, and up to like number 70, and you try to keep the photon at this time, which is, you know, it's limited by the Q of the cavity, and I assume we can do that. And then you turn this beam splitter on and off. That means you couple the qubit. So
so I understand. So the normal picture, the picture on the left is basically, that's kind of the optical picture of it going through time. Yeah. But actually the photons are always there all the time. Yeah. So they're just in the resonators. Mm-hmm. So they're always, by definition, in the circuit all the time.
And at the end, of course, you have to count that.
Right. And you do the dynamics by turning on and off the beam splitters in time. Okay. Yeah. I get it. Thanks.
Yeah, Tsai-san, thanks for an interesting talk. I had two questions. One is, I think earlier in the talk you had the qubits coupled to a 50-ohm transmission line. Is that right?
Yes. Yes.
Yeah. What was? Can you remind me what was the extinction that you were seeing on the reflected pulse if you drove the qubit?
For this, you're talking about. I believe this is single photon generation.
Yeah.
Reflected pulse.
Yeah, like if you excite it, then the there's ideally 0% transmission, 100% reflection. So I was just wondering what the...
Yeah.
So I can...
Yeah, right. So you are, if there's a qubit and the transmission line, 1D, and at the resonant point, everything 100% will get reflected.
Right, right.
And this is what you're referring.
Yeah.
And in this particular case, not exactly like that. Let me go up. It doesn't go back. But anyway, yeah, okay. So when this is excited and it decays, the photon, because we have a very large asymmetry of the coupling.
Yeah, I see. It's not a 50 ohm transmission line. There's capacitive.
Yeah. So
on both
this is
sides.
not
Yeah, I see.
exactly.
Yeah.
So this is half. We chop this into half. So
Yeah,
it's not one open space, but half open space we call.
Okay.
Yeah.
Thank you.
Okay.
Okay, let's thank our speaker.